Hello, I'm John English from California State University, Los Angeles, from the lab of Dr. Alexandra Wright. And I'll be talking about microclimate amelioration and environmental gradients in Los Angeles. To get into it, as I'm sure you're aware, urbanization is rapidly expanding across the globe. Currently, 5% of the total surface area of the United States is urban or built up. And by 2030, this is predicted to increase to 9.2%. And this results in environments that are drastically different from their less developed counterparts, which we can see here in an aerial photograph of Las Vegas taken in 1973, compared to one taken in 2010, where the changes in land use are very significant. And so an open question in ecology is, how do these changes affect biodiversity and ecosystem functioning? What we currently see in the literature is a peak in total species richness at intermediate levels of development. And so in this meta-analysis by McKinney et al., we see that the vast majority of studies find peak plant diversity in suburban areas that have this intermediate level of urbanization. This occurs because there's an introduction of species faster than they're being lost in these areas. Additionally, there's many different land uses. So there's high spatial heterogeneity, resulting in many different microhabitats for species to occupy. There's also a higher availability of limiting resources in urban environments. And in semi-arid locations like Los Angeles, there's a greater importation of water. Additionally, there's higher fertilizer runoff and atmospheric nitrogen deposition, which is important for plant systems given that nitrogen is one of the most limiting resources. We also see that exotic species introductions are higher in urban areas, where in the study by Avolio et al., which was done in Los Angeles last year, we see that in natural remnant areas, there's a greater proportion of native species to exotic species, where when we then move to cultivated, more urban areas, there's a greater proportion of exotic species. This happens because exotic species may be more stress adapted, urban areas having higher levels of stress. Additionally, there's also the modification of natural habitats that results in the loss of native species that have high habitat specialization. We also see the development of heat islands in cities, which are these pockets of heat around developed areas. And in Los Angeles specifically, we see average temperature being 5 to 7 degrees Celsius warmer in city centers. And these temperature gradients may be changing interactions between species. What I mean by this is that we see competitive interactions ubiquitously across ecosystems. Individuals are always competing with their neighbors for limiting resources. Co-occurring with these interactions are facilitative interactions, or positive interactions between individuals. An example of which is microclimate amelioration, and an example of this is that plants can mitigate the water stress of their neighbors via shading and evaporative cooling, which is particularly important in hot and dry systems, where vapor pressure deficit, or VPD, can become very intense. And VPD is essentially a measure of how hot and dry conditions are. And if conditions become too hot and too dry, it can increase the mortality of plants. And so in some research done by my advisor, Dr. Wright, here on the x-axis, we have increasing daily VPD, so it becoming hotter and drier. On the y-axis, we have microclimate amelioration, or essentially the ability of the vegetation to mitigate and cause those temperatures to decrease. And what we see is that on days that are hotter and drier, the vegetation is better able to mitigate those intense conditions. And so this may be operating off of the stress gradient hypothesis, meaning that moderate environmental stress can actually lead to a higher importance of facilitation. So on days that are hotter and drier, it's more impactful that the vegetation is able to mitigate these intense conditions. And in this study, we're suggesting that urban temperature gradients may be imposing a similar stress gradient. So to get into our study, we came with two hypotheses. The first related to diversity, which is that we expected there to be peak diversity in suburban areas, following a loss of native species along an urban gradient, and an increase of exotic species along the same gradient. And so in these suburban areas, we expected to see the most diversity, the most species. To get into the interactions part of this talk, we also expected there to be changes in microclimate amelioration, with microclimate amelioration being weaker in cooler areas and stronger in hotter areas. So these heat islands should have a stronger importance of microclimate amelioration compared to more rural areas where it's less important. So we conducted this study by using the software ArcMaps and selected potential field sites along these following ranges, and then categorized the output of this into urban, suburban, or rural based on the percent impervious surface, which we later validated with a calculated measurement. Then we went out to these locations to ensure that they were unmanaged, unmaintained grasslands that didn't have any sort of management associated with them, which resulted in 27 total field sites, which we can see here across the county, with yellow being our urban sites, blue being our suburban sites, and red being our rural sites. And we can also see an example of what all of these look like. Again, all of them looking quite similar to each other, even though they're across this urban gradient. And so we went to these field sites from April 8th to 22nd of last year, and at each quadrat, shown in the pictures here, we took percent cover measurements. So we identified all of the species occurring at these locations and in what abundances they were. In order to collect data about our microclimate, we used iButton data loggers to record temperature and humidity at 5-minute intervals. And so we had 2 of these data loggers at each site. We had one that was below the grass canopy to determine the microclimate conditions, and one that was nearby, just in a bare patch of soil to determine site conditions, which we could then compare our microclimate to. Getting into our results, our first question, how does development affect diversity? Here, we have percent development on the x-axis and alpha diversity on the y-axis, so a measure of how many species are at each location. And what we found was that there was an overall reduction in total species across our urban gradient. We didn't see a peak of species in suburban areas. And so why was that? Here, on the left figure, we have percent development and the number of native species on the y-axis. And what we saw was what we expected, was that with increasing percent development, there was a reduction of native species. However, when we shift to looking at exotic species on the right, with increasing percent development, there was no effect on exotic species. Exotic species performed just as well in rural areas as they did in urban areas. And so since there wasn't that increase of exotic species, like we've seen in previous literature, we just saw an overall reduction in species across our urban gradient. To get into our second question, which was how does urbanization affect species interactions, specifically microclimate mitigation? So to break down this figure, here on the x-axis we have average day temperature, and so this is the temperature on a day at the site. On the y-axis we have our microclimate amelioration, which is the difference between the ambient temperature at the site and under the canopy. And so if data were to fall along the 0 line, that hashed red line, it would mean that it's the same temperature under the canopy as it is at the site. If data were to fall above that line, it would mean that there is a warming effect by the vegetation, so it's warmer under the plant canopy than at the site. And if data falls below that line, there's a cooling effect by the vegetation, where it's cooler under the canopy than at the site. And each one of these points of data represents a specific location on a specific day and its associated temperature. And what we saw was that on days that were hotter, there was a greater ability of the vegetation to mitigate those intense conditions, and they were able to cool the effects of these hotter days better. We saw the same relationship when we look at VPD, that measure of how hot and dry conditions are, which can cause mortality in plants. We saw it on hotter and drier days. There's again this ability to mitigate these intense conditions. So to conclude, we saw that urban systems can change plant communities and diversity, and we saw that native species declined while exotic species remained constant. But we also saw that urban systems are also changing the way that these species are interacting, and that microclimate mitigation was stronger with this urban temperature gradient. And so successful conservation will need to account for changes in local conditions, but also changes in local interactions between individuals. And with that, I'd like to thank my university and everyone from the Wright Lab, and thank you for your time.